Hello, a very good morning to all of you. So, today is the fifth lecture of rate processes. So, we completed two aspects. One is reaction rates and rate laws. Next, we completed effect of temperature on reaction rate. So, today we will focus on complex reactions. So, before going into the details of this thing, what is meant by a complex reaction? We will try to learn first and then we will move on to various types of complex reactions. Now, an elementary reaction is a chemical reaction in which one or more of the chemical species react directly to form products in a single reaction step. So, that is basically a total chemical reaction may be subdivided into small smaller type of chemical reactions. Okay. As for example, if we concentrate on this reaction like H2 gas plus Br2 gas, it is a gas phase reaction to produce twice HBr. So, this reaction has got a mechanism which is known, which has been established by various other means. So, which is known to follow the following steps, that is, first Br2 undergoes homolytic cleavage to produce two bromine radicals or bromine atoms. Then one of these two bromine atoms then will react with dihydrogen, that is H2, to produce one hydrogen atom and a HBr. Then this hydrogen again will react with Br2 to produce Br and another hydrogen bromide, and then this Br again will react with Br to produce Br2. So, these are elementary reactions. So, there are four elementary steps for this reaction. This is the net reaction. You see, this is the net reaction. If you add this total, then you will be getting. So, these two will cancel over here. Okay. Then these two will cancel. Okay. So, in this way, I mean and you see that there is one bromine, that is these two are cancelled, then this bromine and that bromine will cancel. Okay. So, to give you Br2 plus H2 producing twice HBr. So, how this reaction mechanism is established, this part I will discuss in detail maybe in some other lecture, but just to show you that a complex reaction, this is a complex reaction. Okay. So, this complex reaction consists of four elementary steps. Okay. So, an elementary reaction is this is an elementary reaction. So, an elementary reaction is a chemical reaction in which one or more of the chemical species react directly to form products in a single reaction step. This is a single reaction step. Okay. So, in kinetics, a complex reaction simply means a reaction for which mechanism comprises of more than one elementary steps. That means, if it is a complex reaction, at least two of such elementary steps. Such means like maybe at least two elementary reaction steps will be there. And here we will focus on a range of different complex reactions. Okay. So, basically if there are more than one elementary steps, we can call that reaction to be a complex reaction. That is that the reaction is not a simple reaction, its mechanism is not simple. The types of complex mechanisms are like consecutive reactions, or it is also called as sequential reaction. Then competing reaction, that is one reaction is competing with another. Consecutive means A is giving rise to B and then B is giving rise to C. So, consecutive, that is sequential, A to B to C, that is a sequential process. Another situation is pre-equilibria. Next, it can be unimolecular reaction. So, I will come to the point what is meant by molecularity. It is a bit different from the concept of order, because order is an experimentally derived quantity and molecularity is a theoretical concept that is based on number of species involved in an elementary step. Okay? So, in this case it is a, you see there are two species, two bromine atoms. Okay? So, it is basically bimolecular, I mean biatomic you can say, or maybe here like H2 and Br, it is a bimolecular process. Okay? So, unimolecular, bimolecular, like unimolecular reaction is a complex reaction. Then as I gave you some idea in earlier classes that enzyme reaction, it is also not a simple reaction, it is also a complex reaction. Then chain reaction means like this radical reactions or polymerization reactions. Okay? So, these are chain reactions. So, chain reactions are also complicated, that is complex reaction. Explosion, as I told you that with increase of temperature after certain temperature or above certain temperature, there is a huge increase in rate. Okay? So, explosion is also a complex, is a case of complex reaction. Okay? So, consecutive, competing, pre-equilibria, unimolecular reactions, enzyme reactions, chain reactions, explosions, these are primarily complex reactions. So, first let us talk about this opposing reaction. It is also not a simple reaction, you see. So, it is occurring, as I already told you in maybe some other lecture, that equilibrium. Okay? So, equilibrium and reaction. So, equilibrium is always there. If the equilibrium is far shifted towards the right, then it is called that reaction is completed in the right hand direction. Maybe the back reaction is very small. Okay? But basically all reactions, for all reaction you can think of a back reaction, and if the back reaction is appreciable, then this back reaction competes with the forward reaction, and ultimately at certain point of time you may get equilibrium. So, reactions occurring in forward and reverse directions are called, means these are simultaneously occurring, are called opposing reaction. You see A to B, so forward rate constant is K1, reverse rate constant is K minus 1. Okay? So, when reaction has just started, that is at T equal to 0, the concentration of A is Ca0, 0 means at T equal to 0, and at T equal to 0 the concentration of B will be 0, because it has not been formed, it is yet to be formed out of A. Okay? So, rate of disappearance of A can be written in this way. You can look into the slide that dC A dt is this K1 Ca minus K minus 1 Cb, because this is the concentration of B, this is the concentration of A, and so you can write in this way that K1 Ca minus K minus 1 Ca 0 minus Ca. Okay? So, at equilibrium what we get? Basically Ca0 minus Ca, this is Q is bigger, actually this will be Eq small like this. Okay? So, this you can write at equilibrium, you will be getting Cb equilibrium by Ca equilibrium is equal to K1 by K minus 1, which is nothing but equal to concentration equilibrium constant Kc. Okay. Then from this you can get Ca0 is equal to K1 plus K minus 1 by K minus 1 Ca equilibrium. Okay. And then substitute this into the rate equation. What was the rate equation? Rate equation was this. Okay. So, if you substitute this into the rate equation here, this one, if you substitute this, the expression for C, that is, if you replace Ca0 in terms of Ca equilibrium, that is the equilibrium concentration of A, then you will be getting this expression. dCA dt is with a negative sign is equal to K1 plus K minus 1 times Ca minus Ca equilibrium. Okay, that is, this is the concentration of A at equilibrium when the backward and the forward rate, these two are equalized. Upon integration, we get this. Upon integration, we get this. Okay. Now, if we plot, because this is a Ca0 minus Ca equilibrium. So, equilibrium concentration has got some number, this is the starting concentration, this is the variable. Okay. So, if you plot ln Ca minus Ca equilibrium, E means equilibrium, this is equilibrium versus T, you will be getting. So, plot of ln Ca minus Ca equilibrium, if you plot this versus T, you will be getting a straight line. You will be getting a straight line. Okay. So, from this straight line, what do we expect? So, you see, your expression is ln Ca0 minus Ca equilibrium divided by Ca minus Ca equilibrium is equal to K1 plus K minus 1 into T. Okay. So, this is your slope, this is your slope. Okay. So, slope you will be getting, I mean from this plot. So, this is your slope. So, from this plot you will be getting K1 plus K minus 1, and your equilibrium constant that is Kc can be determined experimentally. Experimentally means equilibrium constant, there are various ways of finding out the equilibrium constant. Okay. So, Kc is equal to K1 by K minus 1, that can be experimentally calculated or obtained. Okay. So, if we now combine this slope and this, we will be separating out K1 and K minus 1, that means we can find out K1 and K minus 1. So, what is the prescription? Prescription is that ln Ca, so this is an opposing reaction. Okay. So, this is an opposing reaction, okay, with forward rate K1 with a backward rate or reverse rate K minus 1, and then we will plot. What we will do, experimental, we will have an experimental plot, that ln Ca minus Ca equilibrium versus time. We plot this, we will be getting a straight line. From this straight line, we will be getting the slope, which is nothing but equal to K1 plus K minus 1, and equilibrium experiments will be giving you, the K1 by K minus 1 number. So, from these two you will be able to find out the forward rate and the backward or the reverse rate. Okay. Let us have an example, that dissociation of water. So, water, it is HOH. Okay. So, it dissociates heterolytically to give you H plus and OH minus. Okay. So, with a forward rate K1, reverse rate K minus 1. Okay. So, K1 is known to be K1 is known to be of the order of 2.4 into 10 to the power minus 5 second inverse per second, this much. We would like to find out K minus 1 is equal to how much. So, what to do? How to find out K minus 1? So, as I told you in last slide that the prescription is that we should know the equilibrium constant Kc, that is the concentration equilibrium constant. It should be known, and we have got this one. So, from this we should be able to find out K minus 1. So, Kc is equal to H plus concentration divided by OH minus into OH minus concentration divided by water concentration. Okay. So, this is this H plus OH minus, if you recall pH, ionic product of water, then this will be 1 into 10 to the power minus 14 at maybe 25 degree centigrade, and water has the concentration in molar concentration 55.5 molar. Okay. So, this gives you 1.8 into 10 to the power minus 16 mole. Mole per decimeter cube means equilibrium, it is basically equilibrium constant should not have any unit, but it is just to show that it is expressed in mole per decimeter cube. Okay. So, mole dm to the power minus 3. So, it is not the unit of a thermodynamic equilibrium constant, because thermodynamic equilibrium constant does not have any unit, but this is just to remember that it is mole per decimeter cube. Okay. So, K minus 1 will be equal to K1 by Kc, which is equal to 2.4 into 10 to the power minus 5 divided by 1.8 into 10 to the power minus 16, which is equal to back reaction. Okay. So, 1.3 into 10 to the power 11. Okay. It is a back reaction. So, it has got this huge number. Okay. It has got this huge number. So, that means if you think that it is a tremendous back reaction, you see it is 10 to the power 11, back reaction is of the order of 10 to the power 11, and the forward reaction is 10 to the power minus 5. So, it is a very feebly ionized, it is mostly in water form, Okay. So, it is predominantly back reaction is predominant than the forward reaction. So, in this particular discussion, just do not consider these units, this is just to remember that in which unit these things are expressed. Okay. And here also you get the appropriate unit from this mathematical expression, because it is a dimensionless quantity. So, it is having a dimension per second. Okay. So, that means it will also have a per second kind of thing. Okay. So, anyway, and also in this case one important point is that, so these units you should not recall from here, means from here you should get the actual kinetic expression, and from that you try to devise, you try to find out what should be the unit for this minus 1. Okay. So, it is for your practice, you can try. Okay. So, basically you do not use these dimensions over here. Okay. You try to find out by your own the dimensions. Okay. And also try to check whether these dimensions are okay or not. You will be finding that this Kc should not have any unit. Anyway, now if if K minus 1 is very small, okay, here in this case for this reaction K minus 1 is huge compared to K1. So, if this is very small compared to the forward reaction, then Ca equilibrium will be very close to, that is Ca equilibrium means this one will be, I mean left hand side will be very close to 0, and your expression will get simplified into this ln Ca 0 by Ca is equal to K1 into T. Okay. Let us move on to the next slide, that parallel reaction. Okay. So, what is a parallel reaction? Parallel reaction means a reaction maybe a substance which is undergoing a reaction, okay, to give you B, say A is giving you B, A is giving you B, and maybe there is a possibility that the same substance is also undergoing another process, that is a parallel process, that is not giving you B, but it is giving you C. Okay. So, that means this reactant A has got parallel reactions, okay, has got parallel reactions like with a forward rate of K1 giving you B, and with another forward rate K2 giving you C. Okay. So, that means A is giving you, it is also called a competing reaction, that is they are competing, and whether this particular step will be predominating or this particular step will be predominating, that is determined by this rate constants, that is K1 and K2, whether this will be predominating or that will be predominating. Okay. So, grossly if these two are almost close to each other, then both will be happening almost with equal probability, but if there is a difference in magnitude of K1 and K2, then the situation will be different. So, rate of formation of B, that is dCb dt is equal to K1 into Ca. Okay. So, formation rate will be K1 into Ca, and also the same way rate of formation of C dCc dt is K2 Ca. So, the overall rate of, so basically we are writing in terms of product formation. So, if we talk in terms of A, because A has got two channels, one is this channel, another is this channel. So, overall reaction, I mean overall disappearance of A, that is minus dCa dt, okay, is equal to dCb dt plus dCc dt, because it is a sum of these two, sum of these two rates. Okay. So, if you write, then it is written like K1 Ca K2 Ca, that is K1 plus K2 into Ca. So, overall reaction, overall reaction means it is basically we initially assume that this is a first order kinetics. So, overall reaction, overall disappearance of A is the sum of the individual disappearances, that is why K1 plus K2 is coming here as the overall K. So, overall K will be the sum of the individual first order K's. Okay. So, the integrated rate expression, so if you integrate this one, so integrated rate expression will be like, will be at t equal to 0, at t equal to 0, Cb and Cc, these are 0. Okay. So, if you integrate, you will be getting this expression, that is ln Ca0, that is this is your initial concentration at t equal to 0 is equal to K1 plus K2 into 2 T. So, this is basically like a first order, you see ln A0 by A is equal to K into T. Only difference is that it is a sum of the individual K's, K values, okay, sum of the individual K values, and this happened only because of the fact that both steps elementary, it's like elementary step. So, both steps are first order. Okay. So, if we plot, then it is like this. Ca0, it is the starting concentration, it is depleting to give you some A, So, A is reducing with time, and B and C, these two are exponentially rising. Whether this will be produced in larger proportion or this will be produced in larger proportion, that is decided by the their relative rate constants, that is the magnitude of K1 and K2. Okay. So, you can if you want to find out Cb by Cc, that is this one, Cb by Cc. Okay. So, concentration of B by concentration of C, then it will be related by K1 by K2. So, combining K1 by K2 and K1 plus K2, K1 by K2 means this is basically what? Combining K1 by K2 means this is concentration of equilibrium concentration of B by C, maybe you can think in that way. So, combining K1 by K2, this one with K1 plus K2, because K1 plus K2 will be getting from this plot, okay, ln 1 by Ca versus T, you will be getting a straight line, okay, and from the slope you will be getting K1 plus K2. So, if you combine K1 by K2 with K1 plus K2, you can find the individual values of K1 and K2. So, the point is that it is also acting like a first order decay of A. Only difference is that this A is decaying in two parallel channels B and C. Okay. Now, if we think of temperature, what will happen? Now, as I told you in earlier lectures that high temperature is favorable to the reaction with a large activation energy. Okay. That is the reaction which is having very high activation energy, that reaction will be favored if the temperature is increased, and the low temperature, that is the lower temperature, will favor the one, that is that reaction which is with relatively lower activation energy. With this means you can recall this expression and you can get a justification of this statement. Okay. Next, we will move on to consecutive reaction. Consecutive reaction means it is a sequential process. It is a sequential process, that is, you have got A, it is the starting material, that is giving you B, then B will be giving you C, okay, with K1 and K2 rate constants. Okay. So, at T equal to 0, Ca 0 it is, this is 0, this is 0. At T equal to T, this is Ca, that is the concentration of A is Ca, and this is Cb, and this is Cc. Okay. So, this way reaction will follow. So, at the very start, no B and no C is there, only A. The moment reaction has started, so slowly this will be produced, and when the concentration of B is appreciable, then B will again start to get converted to C. And in this case, we must remember one point, that maybe there is a possibility of B to go back to A, but in that case those possibilities are neglected, maybe because that may happen, but with such a lower rate that is not we cannot consider that. There is no point of considering such a lower rate. So, that is why this reaction is primarily A to B to C. Okay. So, reactions occurring in sequence known as consecutive or sequential reaction, in which the product of one step becomes itself the reactant for further reaction. So, this one is the product of A, this is becoming a reactant for this product. Okay. So, dCA dt is equal to K1 into Ca. So, dCA dt with a negative sign is equal to K1 into Ca. If we integrate, we will be getting that Ca after integration. This is a differential equation. When we integrate, we will be getting Ca is equal to Ca0 exponential minus K1 t. So, basically minus K1 t means with increase of t, this quantity will be depleted. That means Ca will be decreased in a first order fashion, exponentially decreased. Okay. So, this is concentration at this time. Okay. Now, dCbdt. Now, let us find what will be dCbdt, that is the rate of formation of B. So, ddt of Cb, okay, because we are looking at the formation rate of B, that is why it is in plus sign, is equal to K1 Ca. Recall the initial prescription that A to B to C K1 K2. So, B is produced with K1 rate, that is why it is in plus sign. This is depleted with K2 rate, that is why it is in minus sign. So, minus K2 Cb. Okay. So, that means recall the earlier result that Ca is equal to Ca0 into exponential minus K1 t. So, that you just plug in over here. So, Ca0 into exponential minus K1 t minus K2 Cb. Okay. So, the solution will be like, if you get the solution, it is an ordinary differential equation. Your solution will be Cb is equal to K1. You can try this by yourself. Ca0 divided by K2 minus K1 exponential to the power minus K1 t minus exponential to the power minus K2 t. Okay. And also dC dt is equal to K2 Cb, because the C is produced only from B, only from B. That is why this has got only one term, only single term. Okay. And also Ca0 is equal to Ca plus Cb plus Cc. So, instantaneous is A, B, C. Okay. At any moment the remaining A produced B and produced C, or maybe remaining A, remaining B and produced C. Okay. So, then the concentration of Cc will be equal to Ca0, this will come out like this, 1 minus 1 by K2 minus K1 into this exponential quantity. Okay. So, exponential quantity, there will be two exponential quantities. Okay. K2 exponential minus K1 t plus K1 exponential minus K2 t. Okay. Basically, this one will be K2 exponential minus K1 t plus K1 exponential minus K2 t. Okay. So, now if we focus on to concentration of various species present in solution for such a consecutive first order case, then we can have three situations. We can have three situations, that one is K1 is close to K2, that is A to B to C, K1 K2. So, these two rates, rate constants are very close. Then the plot will be like a typical plot Okay, this is concentration C, this is time. So, this is your A. So, it is depleted because anyway it is depleted to B in a first order kinetics, therefore, it is always decaying like this. Okay. And your B will be, it is growing, okay, it will grow, but the problem is after it has grown to certain extent, maybe to such a concentration, then this reaction becomes appreciable. When this concentration is low, then maybe it will still doing this reaction, still be doing this reaction, but the thing is that if it is not appreciable, this concentration is not appreciable, the effect of this step will not be we will not be able to feel the effect of this step. That is why up to certain point it will keep on rising and then eventually it will decay because of the second step of K2. Okay. And what about the C? C will follow like this. Okay. So, this is your C, this is your A and this is your B. Okay. So, when K1 and K2, these two are almost close to each other. Okay. And when as these two are close, that is why maybe the maxima is in the midpoint of this graph, maybe this maxima is at the midpoint of this graph. Okay. So, why this is showing a maxima? Because it is growing, this step is a growth factor for this B, that is a. So, this particular step is imparting a rising trend on B, and this one is a decaying trend. So, when rise and decay these two match, then or when they compete with each other with equal strength, then that is neither rise nor decay. That is why it is passing through a maxima with a slope, that is with a slope, that is dc dt, dc b dt is equal to 0. You see here this is B. So, here dc b dt is equal to 0, that is with time the concentration of B is not changing. Okay. So, this is one situation where K1 is very close to K2. Now, let us move on to another case when K1 is greater than K2, that is the effect of this step. So, A to B to C, K1 K2. So, that means this is very strong, this is relatively weak, that is why K1 is very greater than K2. Okay. So, what will happen if we plot? So, A will be as usual with a decaying trend. So, A, this concentration versus time, and this maximum will be near your this axis. Eventually, it will decay, and your this one will be something like this. So, this is your B and this is C. So, this is B and this is C. Okay. So, why it is like this? Because since K1 is very high, therefore, with a very high rate it will reach the top. Okay. In previous case, the maximum was at some intermediate time here, but here this maxima is here much earlier than this maximum. Okay, when this is for your K1 is close to K2, and here K1 is very greater than K2. So, that is the effect of K1 is so high that it gives you this maximum here, and then it is depleted. After a certain time, it is slowly depleted. Okay. And C is as usual, it is going up, that is kind of an exponential growth. Okay. So, again this is also a case where this is a rising function and that is a decaying function, that is why it is passing through a maximum. Okay. The third case is K1 is very less than K2. Okay. So, very less than K2 or maybe less than K2. Okay. So, this is concentration versus time. So, A is as usual like this, exponentially decaying, and what will happen to B, because it will not show a prominent maximum, because the moment it is created, this B is created, it is quickly depleted to C. So, A to B to C. So, concentration of B is not built up to a sufficient extent, as a result of which this one is less, that is your maximum concentration, or I mean T at which this CB is maximum, it takes long time, okay, because it is slowly growing and it is fast decaying. Okay. And as usual your C is like this. Okay. So, this is A, this is B and this is C. So, these are the three possible situations that one can think of. So, then how to find out this maximum concentration of the intermediate, okay, or maybe the time when this reaches the maximum. So, it is easy, as I told you, that if we have a plot for this B, it is like this, maybe it is a typical plot. So, concentration of B versus T. So, dCB dt will be equal to 0, dCB dt will be equal to 0. Therefore, what we have to do is, we have to, this is called the extremum situation. So, you have to find the extremum condition. So, dCB dt is equal to K1 Ca 0, recall earlier slides. So, K2 minus K1, then K2 exponential minus K2 exponential. Okay, let us go back to earlier slide. dCB dt, this is your dCB dt. Okay. So, we have to use this expression. So, K2 exponential minus K2 t minus K1 exponential minus K1 t, you just recall, equal to 0. So, equal to 0 means this is 0, this is 0 means T max, that is for T equal to T max. So, T equal to T max, so T max will be equal to ln K2 minus ln K1 by K2 minus K1. Okay. So, CB max will be equal to, that is the concentration of B at T max. So, CB max. So, maximum concentration of B will be equal to Ca 0 K1 by K2 into K2 divided by K2 minus K1. So, what is the utility of such a description? Okay. This has got a tremendous utility, that if you think of industrial processes, like A which is producing the desired product B, and then your desired product may undergo some side reaction or maybe some other reaction which is an undesired one, which is useless, maybe which is useless to you. Okay. And also think that maybe this step, these two steps are first order for simplicity, and also K1 is greater than K2. K1 is greater than K2 means the case which you discussed. Let us go back to this slide where these plots are given K1, K2. So, we will refer to this plot maybe. Okay. So, our question is at what time will product B have the highest yield? That means, we have to calculate that time, and then maybe we have to isolate your reaction mixture maybe during that time, when means your calculated time say maybe after 1 hour of your start of reaction. If you calculate that your concentration of B will be maximum, then just after 1 hour you just take out your reaction mixture, okay, and then you try to isolate your B as early as possible, so that you will be getting the maximum yield of B. Of course, with the condition that K1 is greater than K2. Maybe if K1 is less than K2 or something else, then the situation may be different. So, what we will do? We will first look into time evolution of B, that is time variation of B. So, dV dt is equal to, as I gave you the expression that K minus K1 A0 means your starting concentration, K2 minus K1. So, you have to like do this exercise, of course, with the assumption that this step is first order, this step is first order. If it is not first order or something else, then you cannot help with this expression, with these equations. You have to think of something else. Okay. So, that means you have to extremize it, because you would like to find out this the condition when this happens, like this happens. So, the idea is that you have to look for this one. Okay. So, this is concentration versus time. So, you just extremize it. Okay. You extremize it. So, upon extremization, you put that equal to 0, and also that that your A0 is not 0 and K1 is not also 0. Okay. K1 is also not 0. So, with those conditions, as I told you that this is already stated that Tm maximum is equal to ln K2 by K1, K2 minus K1. Okay. So, you can find out the maximum concentration of B, that is B maximum, which is like this. B max is equal to this, as I just wrote. Okay. So, this way you should be able to find out, to find out the maximum concentration of B. Okay. So, for K1 greater than K2, as K2 increases, okay. So, if K2 increases, then what will happen? So, this K2 increases. If K2 increases, okay, what will happen? So, this increases, okay, this increases and this also increases. So, this increases means this denominator is becoming less and this is increasing, and this is increasing, although this is increasing means this factor is increasing, but as a result of which what will happen, that since the power factor is more to the power factor, so both time when, so as increases both the time when B is maximum and the yield of B, these two will go up. Okay. So, that is why there is a relation, because this relation gives you how you can modulate this B max. You can modulate this B max by changing, somehow if you can change this K2, maybe by increasing temperature or something else. Okay. So, that is why for K1 greater than K2, as K2 increases, both the time when B is maximum, okay. So, this is B is maximum and also yield of B, these two go up. Okay. So, that is why consecutive reaction, it is a very, although it is I have discussed this first order case, but anyway this is just to give you the idea that if side reactions are happening, like consecutive reaction of which, suppose this reaction, the reaction with which we have started our talk with, with consecutive first order reaction, that say this is your desired reaction and say this is your side reaction. If you think that this is your side reaction, then it is a real problem, an industrial batch production. So, this is your headache. So, in that case what you have to do, you have to just tactfully calculate, you have to calculate this time when B is maximum. Okay. So, if B is maximum means the time when B is maximizes. So, at that time you try to isolate, your reaction mixture. Okay. So, you try to isolate your reaction mixture and then try to work up means try to recover your B product. Okay. So, these are very important. So, you see this consecutive reaction has got a very this has got an immense importance in industrial preparations. Okay. So, what we have learned in this particular discussion on complex reaction. Okay. So, first we have to recall this thing, what is an elementary reaction. It is a very important point. Elementary reaction means a complex reaction. A complex reaction can be regarded as a combination of more than one elementary steps. Okay. So, elementary steps means at least it will have 2 elementary steps, and elementary steps are steps where you can just see as if 2 components or maybe one component is directly giving you the product, So, see as you see here the example with which I have started the discussion, that this particular reaction has got 4 elementary steps, and you see 2 species here, 2 species, 1 species. So, these 3 are bimolecular step. This is an unimolecular step you can call. Okay. And we have classified this complex reactions like consecutive reaction, competing reaction, pre-equilibria, then unimolecular reaction. Another is bioreaction, that is enzyme reaction, enzyme catalyzed reaction, chain reaction, we will come to that in later lecture, and then explosion. Okay. Then we have discussed this opposing reaction, that is one reaction which is opposed by another reaction producing your reactant back. Okay. So, and also from this studying this opposing reaction kinetics, we can find out the K for both forward and backward steps. Of course, we have to know the equilibrium constant, and that we can find out from other measurements, that is equilibrium measurements. We have given an example. Of course, be careful about these units. Do not use these units. This is just to make sure that which unit we are using for calculating it. Okay. So, forget about this unit, try to find out units for these steps by your own. It is not a difficult task. Next is parallel reaction. Parallel reaction, what we have discussed over here is parallel reaction of which both parallel steps are first order type. So, it is a simple first order parallel or competing reaction, and basically your reactant is depleted in first order kinetics and the products are formed, that is products of parallel reactions formed like a exponential growth, and you can also find out K1 and K2, of course knowing K1 by K2 for this parallel reaction. And of course, temperature has got an immense importance on which step will be favored or not, that you can find out using this Arrhenius equation. Consecutive reaction, it is A to B to C, where B is an intermediate maybe, or maybe it is your desired product also. Okay. So, with K1 and K2. So, under various conditions, when K1 is greater than K2 or K1 is lesser than K2 or K1 is equal to K2, you can find out the situation which is depicted in the graph like case 1, case 2 and case 3. Okay. So, every case you are finding that this B is passing through a maximum and A is depleting and C is growing, because B is the intermediate which is formed out of A and it is depleted to give you C. So, and this has got importance in your industrial application, that you can find out the time at which this intermediate will be maximum or not, at what time it is maximum, that you can find out, and from that you can get your desired product at the maximum yield. Means after that time, suppose if you calculate the time Tm, after Tm you can in principle find out the the desired product, and means when this desired product will be in maximum concentration. Okay. So, in our next lecture we will talk more on complex reactions, and we will take up like other reactions I just pointed out when we started this particular lecture. So, till then have nice time, and we will meet in the next class with more example on complex reactions. Thank you.